nichol, and it's got a rhythm compound, and the usual time and the 10 minutes of question.
Okay, well, can everybody hear me at the back? I'm going micless. Okay. Thanks for inviting me. It's a pleasure to come back to Stockholm. I was here, I guess, a year ago. Actually, a lot has happened in the last year, and I'd like to give you an update from the Sloan Digital Sky Survey on both the supernova part of that survey and also on the baryon acoustic oscillations from that survey. So there's some very interesting stuff that has been happening in both of those arenas. Thus, the title, wiggles being the baryon acoustic oscillations, and bangs being the supernova. So I didn't put my name on the front slide because obviously these surveys now are done by many people, and I am simply a cog in a big machine, and I'm the lucky one you have today, but there are many people working within the Sloan. I will also touch upon the DES and WIFMOS teams during this talk, so you should direct all your comments and all your questions to these teams. Okay, so this is my one slide about dark energy. Luckily, you've heard quite a bit about dark energy already. I'm going to give you sort of an observer's perspective on trying to understand this thing called dark energy. And mainly, I think as an observer, we've sort of coined these two questions that we can try and go after as observers or experimentalists. So the first one is probably you're quite familiar with. That is dark energy just this cosmological constant, which means that its equation of state as a function of redshift is -1, or for the classic Einstein's cosmological constant, it would be -1. So is dark energy a cosmological constant? So we're trying to answer that question now, and the last speaker touched upon this, and the way we try and do that is basically we get better observations, and we try and push to higher redshift. Or maybe I shouldn't say push to higher redshift, we try and get observations across a range of redshift. I think there's actually quite an interesting second question that is now creeping up in the literature, and that is dark energy a new form of matter that we put into our normal Einstein equations and churn through those and get out a prediction? Or do we try and think of something a little bit more radical, which is the breakdown of our understanding of gravity on large scales, and we try a new theory of gravity? And there are certainly people in the audience who are much better than that than I am, and I'm sure you'll hear a lot about things, for example, like brain world models and things like that. And I think the way we can probe those is certainly to try and look at dark energy through many different probes. We don't just want to pick one probe. By looking at the differences between the probes of dark energy, we might see a signature of this breakdown of general relativity. And here I sort of list the two probes we can use. We can use geometrical tests, which are supernova and baryon acoustic oscillations. So this is mapping out the geometry of the universe as a function of distance from us. There are also the growth of structure probes, and this is things like the integrated Sachs-Wolf effect, lensing, and clusters. I won't be talking about these, but clearly there is a very active future in these growth of structure ways of measuring dark energy. So by contrasting these two, we might be able to have an impact on the second question. So, as an observer, what do? I need to go out. This is, by the way, a fantastic time to be an experimentalist. Dark energy has come along, and it's basically told us that we need to study the universe not only as a function of redshift, but as a function of volume. We need lots of volume to measure dark energy. Okay? And as an observer, that allows me to write all those wonderful grant proposals saying, I need a brand new instrument to go out and measure lots of volume in the universe, so please give me lots of money. Okay? And that's basically what the next 10 years is going to be like. All right, it's going to be me writing lots of grant proposals for lots of money. Okay, so if you get my proposal, please say yes. All right. So, so we need lots of surveys to measure this dark energy accurately. The three surveys I will touch upon today will be the Sloan survey, which has gone from the original Sloan survey to Sloan 2, and as I will indicate, is now gone to something called AS2. I'll explain that later. And within that banner, there are actually three things I would love to talk about. I'm only going to talk about the first two, which is the supernova part and the baryon acoustic oscillation part. I have done quite a bit of work on the integrated Sachs-Wolf effect. Don't have time to talk about it today, but please ask me later. I'll also touch upon the Dark Energy Survey, which is now building a brand new camera for the Blanco telescope in Chile, and I'll just highlight the new supernova survey that we're planning with that instrument, which is shown here. And I'll touch upon WICMOS, which is a new instrument to study the baryon acoustic oscillations for high precision. Okay, so the first survey I'd like to talk about is the Sloan Digital Sky Survey. It's a bit of an old survey now. It was started operation in the year 2000, so it's been going now for 7 years. It's a 2.5 meter telescope, 2.5 meter mirror telescope. It sits out without a dome around it, just in the Sacramento Mountains in New Mexico, in the USA, just off the barrier here. If you were standing here looking down, there's White Sands Missile Base there. So in fact, it's quite fun at night to sit here and peer with a pair of binoculars into White Sands Missile Base, and probably get into trouble from the US military. The Sloan survey is made up of two parts. It's an imaging survey using this very large digital camera, and a spectroscopic survey using this fiber thread spectrograph, which are the spectrographs are these green coffin-shaped items on the back of the telescope. We released last year something called DR5, Data Release 5. That released to the community 1 million spectra and 8,000 square degrees. This is almost certainly the largest survey ever done of the night sky, and I do encourage you to go and use it. It's an absolutely wonderful data set, and it's out there in the public domain. There was an extension to the original Sloan called Sloan 2, which has been running from 2005 to 2008. That is made up of something called Legacy, which is just more of the same. There's the supernova component, which I'll talk about in a minute, and there was a galaxy dynamics component that I won't talk about at all. So the Sloan is now doing these three in tandem. So what is the Sloan Supernova Survey? Well, the idea here is that the wonderful thing about this Sloan camera is that in one night, you can basically scan a swath of the sky that is 2.5 degrees wide by about 120 degrees. So in one night, you can observe many hundreds of square degrees of sky. Okay? Sorry, in 2 nights, because you have to do the blue and red. So in 2 nights, you get this 300 square degrees chunk of the sky, and you get it in all 5 Sloan passbands. So basically, what you do is you get 300 square degrees every 2 nights, and you get it in U band, which is the ultraviolet, all the way through to the near infrared, which is basically the Z band. We've been doing this now for several years. We're, as you see from these dates, about to enter our 3rd year, which will be our last year of operations. And basically, we can take the data from one of these scans, reduce it in 24 hours, and find supernova. And I'm very happy to say there's been a lot of telescope time used in the spectroscopic follow-up of those discovered supernova, and a lot of the time has actually come from European telescopes. So thank you to the TAPS from the NTT and the NOT. Okay, so where do we stand right now with finding supernova? I won't go into the details because we just had a wonderful review of supernova cosmology. So here are the numbers from the Sloan Supernova Survey. After 2 years, so this is after 2005 and 2006, we have 325 spectroscopically identified 1As. So these will be what we use for the cosmology. As you see, we have some 10% could be probable 1As from the spectra, but we also have a very interesting group that is growing all the time, and that is things that photometrically look like a 1A, and I mean the fits to the light curves are actually very suggestive. And we also have a host redshift for the galaxy. So this sample here could boost this up to 400 supernova that you could use in cosmology. The key thing, as noted before, is that the mean time between observations of the supernova is about 4 days. So basically, once we've detected a supernova, we observe it every 4 days, and we're able to produce a light curve as shown by the last speaker. So here's, I thought there was going to be a light curve there. I think that's coming in now. Anyway, let me give you some new results from it. So what we showed here now is just the first thing you can ask is, this is just from the 2005 data, so not including all those supernova in the last slide. But you can ask your question, how many supernovae are there per megaparsec cubed, so per year? So this is just the rate of supernova 1A as a function of redshift. And the black line here was taken from, I believe, this is the SNLS line, and the SNLS are the open circles here. So this is the best fit to the open circles. And as you see, this fantastic agreement at low redshift for the rate of supernova detected by the Sloan. You also see the complementarity between the SNLS and the Sloan is that we are measuring this low redshift rate that Renee talked a lot about. So basically, here is the rate that we've measured. This is about, as you see by the error bar, substantially better than the present low redshift rate measurements. So we're finding the right number of supernova, so that's reassuring. We've also now done it as a function of galaxy type, and now what we show here is the star formation rate, or the specific, this is the star formation rate divided by the stellar mass, so this is sort of an efficiency measure, and this is the rate of supernova per unit stellar mass. And what I just want to show you here is, again, we see exactly the same trend as the SNLS. There might be some issue with the normalization here, but I wouldn't claim the red points are above those points because of a physical effect. It's probably just the normalization needs to be tweaked. But basically, we see exactly the same as the original low redshift work, and also now the SNLS. And basically, what we find is there's many, many more supernova in these actively star-forming galaxies. And this again comes back to something that was said by the last speaker, is now there's a very interesting environmental effect with these 1As. There is clearly something that the 1A knows about the galaxy it's going off in. So that's something I think in the future for supernova surveys is that we have to worry about the type of galaxy these supernovas go off in. Well, there was a lovely paper by the SLS where they investigated this very plot, and they came up with a model called the AB model, where there does seem to be something called a prompt supernova and a delayed supernova, in that one of those different styles of 1As go off in different types of galaxies. And I'll show you soon, when you look at the Hubble diagram, there does seem to be some effect of the host galaxy on the Hubble diagram. So I'll show you that in a minute. So yeah, it was shown that the fainter, that the ellipticals contain substantially fainter 1As. So there is a growing environmental dependence. So now in the cosmology, I'm going to not give you the cosmology today. Very sorry. If you were waiting for it, you're not going to get it. I'm not allowed to show you. If I showed you, I'd have to shoot you. Okay? So, which would take a lot of effort. All right. But anyway, I just want to show you again the complementarity between the supernova, the Sloan supernova survey and these other higher redshift supernova surveys that we just heard about, as you see from this redshift histogram, basically the red here is the Sloan, and it wonderfully fills in this gap between the low redshift supernova and the high redshift supernova from surveys like SNLS. So the Sloan, I think, will actually probably become the low redshift anchor for the high redshift supernova. So the low redshift samples that we talked about being the major part of the systematic uncertainty now, as you see, we will probably be able to use the Sloan as that low redshift anchor for the high redshift supernova. So the analysis we're doing right now, here are the numbers that we're talking about. These two are taken out of the literature. We're using 90 supernova just from 2005, and we're using these infamous 44 that are in the literature. So here are some examples of our light curves as a function of color, and as you see, over the redshift range that we are studying, we get wonderful coverage of the light curves as a function of color. Okay? There is an issue with the I band right now, and that is why I cannot show you the cosmology. We're close, but we've still got one or two of those gremlins to figure out. And actually, one of the gremlins is this light curve fitter that was highlighted in the last talk. So I would expect in the next few months you will see this published, but I'm not showing it to you today. All right, let me talk a little bit about the dark energy survey. This is, as I said, going to be a large imaging camera put on the 4 meter at Blanco 4 meter in Chile. And here, the idea behind DES is that DES is now the first of a stage 3 dark energy project. This is terminology used by the Dark Energy Task Force in the US. And the idea is that these stage 3 surveys have to now probe the systematics of the dark energy measurements. Okay? So as pointed out by the last speaker, supernova surveys are becoming systematics limited. So what we want to do with the DES supernova survey is to probe those systematics, to try and understand them, and then allow the stage 4 surveys to either understand them or ignore them. So the idea here is basically the beauty of the DE cam, which is that camera I showed you 2 slides ago, is that it will have fantastic red sensitivity. In fact, to give you an idea of its red sensitivity, DE cam will be better in the Y band than VISTA, which is an infrared design survey telescope by ESA. So in the Y band, DE cam is a better telescope. It falls off very rapidly after Y, but we will be able to go out to about a micron with DE cam. So the idea is because we have fantastic red sensitivity, we can go after the rest frame G at redshifts out beyond this 0.7. So as highlighted in the last speaker, beyond about 0.8, there was this issue with the observing the rest frame U band. With DE-CAM, we'll be able to get rest frame G band light curves out to a redshift of 1. So we won't have to worry. We can use the local G band light curves and have sort of a rest frame G band calibration all the way out to a redshift of 1. So again, that's one of these systematic issues that we've got to worry about. So the idea is to spend 750 hours, survey about 9 square degrees with a cadence of 4 to 6 days in these RIZ, maybe even Y. I think it's looking more and more likely that we'll do this in Y band. The predictions are to find over 1,000 1As over this redshift range, and here basically is what we expect to find here in the red compared to Sloan and SNLS in the black. So as you see, we will do we'll do very well up above redshift of 1. And the question next is how do we follow up all those supernovae? Well, we're not. Right? ATTACK is probably not going to give us time to follow up 1,000 supernovae. So what we decided to do is probably to be quite selective. As we talked about a few minutes ago, there is an environmental dependence on the 1A. And this was shown by Sullivan in 2003, in that basically when you look at the residuals around the best fit cosmology, the red points are supernova going off in ellipticals. And as you see, the RMS scatter around the best fit is lower when you go after the 1As in ellipticals. So what we plan to do is to look at about the 300 1As that are just in elliptical hosts. Those potentially give us the biggest bang for the buck, okay, without having to follow up all those 1,000 supernovae. Okay. We could also try and target high Z clusters to try and get a little bit of a boost in the number of 1As from elliptical galaxies. This is all under investigation right now through extensive Monte Carlo simulations. So I should just show you this this plot, this table, sorry. I just want you to zero in on these two numbers here, and again, if you are on a funding agency considering proposals, this is all you need to know, okay? Is that basically that number, which is the figure of merit for the dark energy survey, is about a factor of 5 bigger than that, and this is the present day constraints on dark energy. So we hope that we will arrive to a factor of 5 improvement in the figure of merit once we've combined all these different probes with the dark energy survey. And the interesting thing here, this supernova part of it, even though the supernova only make up 10% of the time in the dark energy survey, it's delivering a competitive figure of merit. So for all those young people out there, all those graduate students trying to figure out what they want to do in dark energy research, well, those supernova are a good bet. You get a lot for your money, or you get a lot for your small amount of time. Okay, so I'm going to shift gears here and talk about baryon acoustic oscillations. Here I can say something new and interesting, so I won't disappoint you on this one. So what are the baryon acoustic oscillations? Well, I'm going to borrow heavily from a wonderful website I found from Martin White, and here I'm just going to spend the next few slides setting up the physical picture of what the baryon acoustic oscillations are. So what I'm showing you here is an initial fluctuation in the dark matter. This is the black curve in this plot here. This is way before recombination. Okay, so we're well into the primordial plasma here. And basically what happens is this dark matter fluctuation, there is intense pressure within this dark matter fluctuation, and that pressure drives out a sound wave. Okay? So it drives out a sound wave at about half the speed of light. And what I'm going to show you in the next few slides is the propagation of this sound wave. All right? So the next point we take is basically recombination. So before recombination, everything is coupled, but at recombination, what happens is the photons and baryons, sorry, here's the sound wave going out from the fluctuation in the middle, and what happens at recombination is we get the photons and baryons decouple. Okay, so here's the ring of photons, here's the ring of baryons. They're just decoupling at this point. Here is the photons become the CMB that we heard about this afternoon, and I will show you now the subsequent evolution of these two rings. So what happens at a later time? The photons have decoupled, they're just free streaming, they're going throughout the universe, but the baryons are still in their ring. They remain there because there's no pressure anymore. Okay, the pressure is gone, the universe has recombined, and basically the photons have gone their merry way, as you see in this red line here, but we're left behind with this overdensity of baryons on this sound wave. If I go a little bit further in time, what happens again now, the photons have all streamed away, they're almost uniform now, but I still have my overdensity of baryons within the sound wave. But the dark matter in the middle, okay, is starting to pull baryons back. So the baryons in the dark matter, the baryons in the dark matter are starting to go back into equilibrium. And basically we get to today, where the, oh, sorry, don't look at that, don't look at that. Close your eyes. Come on, there you go. So where we get to today is the baryons and dark matter are now back in equilibrium, and what we have is, here's the this final configuration. We're left with an echo of this sound wave, and this echo should be about a radius of 100 megaparsecs. So we would predict today that we should see the remnants of this sound wave at about 100 megaparsecs. Okay? This is a physical scale. Physics has given you a ruler. Okay? This physical scale will feel the expansion of the universe, but it's very much like you've gone to the physics lab and you said, can I have a ruler please that's 100 megaparsecs? Okay? And they've given it to you. Alright? So what we want to do is basically go out and find this ruler. Now the thing is what I've shown you here is this is in real space. Cosmologists like to work in Fourier space, so if I take the Fourier transform of, let's call it a delta function for the sake of argument, it becomes a sinusoidal function. So in the next few plots I'm going to show you, you're looking for a sinusoidal function, you're not looking for a bump. But just think, it's just the difference between being in real space versus being in Fourier space. Okay? So, of course, you don't have a single dark matter blob in the universe and you're going to look for a nice big ring around it. You have lots of dark matter fluctuations, and each one of those is sending out this sound wave. So, courtesy of Daniel Eisenstein, you get this wonderful sort of mottling effect as all those sound waves go out and collide and interact with each other. So you have to look for this signature statistically. Of course, you will never see one of these waves on its own, but you can look for it in a statistical sense. Okay? And the beauty of this baryon acoustic oscillation, from a sort of a systematics point of view, okay, think of this is that you're looking for sort of a sharp feature in the universe. There are not many things that will produce a sharp feature. If you think it might be dust, that usually has some power law form. If it's gravity, it would have some functional form. There are not many things you can think of that will cause a galaxy, cause slight excess of galaxies at 100 megaparsecs relative to 90 megaparsecs and 110 megaparsecs. So basically, you've got this preferred scale, and it's very difficult to come up with a physical mechanism or even a systematic that will produce a preferred scale. Okay, so here is the way it was about a year ago. So this is taken from a paper by Percival et al. In 2006. I would like to point out that there has actually been a very rich history in this, and as you can see, the rate at which the papers have been published is extremely rapid. So the first detection was by a guy called Chris Miller, and there is actually a guy in there called Bob Nichol just after this, so I have to always put this paper. No one ever believed it, so I don't mind, I've got over it. But just in case there's anybody here from the Nobel Prize Committee, okay, I'd just like to point out that we did say back in 2001, you may have seen the baryon acoustic oscillations, all right? So, anyway, these other, actually Max also, in fairness to him, in 2001, there was some indication in the first power spectrum analysis from the slide. So I don't mind, I'll share the prize with Max. Okay, so, so we're going to talk about Percival et al. 2006. What I show here is that wonderful WMAP power spectrum that was shown to us today. This is WMAP 3, and this black line here is the best fit to that data given omega matter of 0.24. So the black line here is the WMAP fit. Okay. The black line down here is the same WMAP fit. So it's the fit to the data up here drawn down here. It is not a fit to the data in the bottom. Okay? But I think you'd agree by eye, it would be a fantastic fit. Alright, so this just goes to prove how wonderful now we're seeing that sinusoidal curve. Remember I told you in real space it's sort of a delta function. In Fourier space you'd expect to see a sinusoidal curve. And that's exactly what we're seeing. These baryon acoustic oscillations, as they call it. This is due to this relic sound wave. This is due to 500,000 galaxies from the sun. So we can also do we can do our cosmology fitting now, and we've done that. I'm showing here two ways we do the cosmology fit. So we say there's a standard ruler. Here we're assuming flatness, we're assuming this H0, and we're assuming this baryon fraction. If you do that, what you see here is as I go from the top panel down to the bottom panel, all I'm changing is omega matter. Okay? Again, by eye, you can see the power of this approach. This here is 0.1. Sorry, I've overlaid it. But omega matter of 0.1, you see we're out of phase, coming into phase, directly in phase, and then going out of phase again. So this is just by eye, again, a demonstration of this standard ruler at work. If you take the best fit of 0.26 omega matter, the detection of just this sinusoidal function is -3 sigma. Okay, so I think we can say we've detected it now. Over here, we've been a little bit more sophisticated. Here we had to sort of assume some of these parameters. Obviously, we can allow these parameters now to vary in a multi-dimensional fit to the data. What I would say is just zoom in on this one. This is sort of our best numbers. If we assume omega matter h squared, which comes from WMAP, that's actually told us from the relative heights of those acoustic peaks in the CMB. So the CMB gives us that. If we assume that, you see that we break the degeneracy between H and omega matter, and this is the best fit to the data. And as you see now, we are below 10% in the measurement of omega matter. Now, I reached my 40th birthday this year, so I feel I'm getting an old man. Okay, I think I'm having a bit of a midlife crisis, but I like to reflect back on my younger years. And in my younger years, when I used to go to conferences, omega matter was somewhere between 0 and just above 1. Okay, so even in my short time in this field, we have gone from a 1,000% measurement of omega matter to a 10%. So the rate of discovery is fantastic. Don't tell anybody I'm 40 there. All right, so here's some new stuff. So we put this out on the web about a month ago, and it's quite remarkable. What we've done now is we've combined the Sloan measurements with the 2DF. So we basically now said, let's get as much data as we can, let's combine it in a coherent way and be careful about all the systematic issues. We've done that, and here is the summary of that analysis. So in the top panel, I'm now showing you the combination of the 2DF and Sloan. As you see from the combination of the two numbers, we're up to 600,000 galaxies. And now we've got 80,000 galaxies, which are called these luminous red galaxies. But the key thing is the mean redshift of these is about 0.2, and the mean redshift of these is 0.35. So we now have two measurements of the baryon acoustic oscillations. So we can now measure the difference in the distance between those two redshifts based on just the baryon acoustic oscillation. We can measure dA versus dZ. Okay, we have one measurement there. All right, and that's basically what we've done here. This is the ratio of distances between those two redshifts based on just the baryon acoustic oscillations. And here is the number we get, and I highlight here, assuming a flat lambda-dominated CDM universe, we get a larger number. right? And that number is tantalizingly 2-ish sigma away. Right? So we are not finding what you'd expect from lambda CDM for the distance between these two redshifts at the 2 sigma. All right? Now, you can get another sigma, so maybe it's only different at 1 sigma because of issues to do with how these acoustic oscillations are damped. Okay, there's an issue with how large-scale structure and peculiar velocities will damp out this sound wave. So the issues of that are now becoming important. And actually, the details of how you fit the baryon acoustic oscillations have now become important. So actually, analogous to the supernova gain, baryon acoustic oscillations are now just entering the systematics-dominated regime. Okay? We now have to worry about these things that we didn't worry about maybe a year ago. All right? And but again, people looking for PhD theses or interesting projects to look at, I think we need a lot more understanding of A, how to fit these baryon acoustic oscillations, and B, what is the physics of this damping. And can we predict that to great accuracy? If we can, then we'll just take care of it and subtract it. All right, so here again is the cosmological fits. So what I show here in the curve, actually the 3 sigma doesn't show up very well, but in the grayscales is the 1, 2, and 3 sigma based on just this ratio of distances. Okay? And if you just use the baryon acoustic oscillations to get this distance, we favor phantom models, so W below -1 to about the 1.4 sigma. All right, so for all the theorists out there, I'm sure they find that quite interesting, and maybe we'll see a paper on Astro PH tomorrow. But anyway, the baryon acoustic oscillation measurement does like, or tends to like, W less than -1. Now, of course, this game is not just about taking one measurement, it's taking all the measurements together and putting them in a coherent way. So what we've done here is if you add in the microwave background, because obviously the microwave background gives you another measurement of this baryon acoustic oscillations, you see that we have, again, the likelihood contours shrink down very quickly. But again, here's the 1, 2, 3 sigma contours. So W of -1 just sneaks in at 2 sigma. All right? But here's the very interesting thing. Of course, we might want to join this with the supernova. We just saw all the wonderful constraints you can get from the supernova. So now I'm going to add in the supernova. Okay? This, by the way, is assuming flatness and a constant W. So if I add in the supernova, everything gets wonderfully consistent. Basically, everything zeroes in on W of -1, and we get a fantastic measurement of W of -1. And again, we get a very nice measurement of Omega Napa. However, this forces the ratio of distances back towards the lambda CDM measurement. So, is there a discrepancy here? Okay, so it depends on your outlook on life, I think. If you are an optimist, I think you see a discrepancy, and great, let's go and figure it out. If you're a pessimist, I think you'll sit there and go, it's 1 sigma. Okay, so yes? So this is just the SNLS. Yes, we did not include the systematics. So are you a pessimist? Okay, that's fine. So as I said, I think, as you see, the optimist would get very excited, the pessimist would say, go back and figure out the systematics. So let me just give you the summary. At its worst, it's a 2.4 sigma difference between the supernova and baryon acoustic oscillations. You could phrase that as the baryon acoustic oscillations are more acceleration in the universe below a redshift of 0.3 than you get from predicting back from the high redshift supernova. All right. So one thing we would love to do and plan to do is the Sloan supernova redshift interval directly overlaps these baryon acoustic oscillation measurements. So we should be able to, in a few months, be able to take internally, be able to take the Sloan supernova over the same redshift range, compared with these baryon acoustic oscillations, and really figure out if this is true or not. As pointed out, there is one sigma. One of these sigmas you can get away if you look at more complex damping functions. Okay, so now 2.4 sigmas down to 1 sigma, and we haven't included the supernova systematics either. So maybe it's just all about systematics. All right. Maybe much more exciting for this audience is that maybe it's a signature of that flat lambda CDM model isn't everything. All right. So I will leave you with that thought. So again, if you're the optimist, I guess this is where you'll be looking. Okay, so where are we going next in the baryon acoustic oscillations? I think basically we've got all we can out of the Sloan. We've got all we can about the 2DF. And where we're going next is with something called the BOSS survey, which is the Baryon Oscillation Spectroscopic Survey, and also known as AS2, which is after Sloan 2. And basically what they want to do with BOSS is do something we did about a year ago called 2SLAC. 2SLAC are LRGs now, which go out to a redshift of 0.8 out here. So you see, this is about 10,000 LRGs out beyond the present Sloan LRGs. BOSS will just fill this in. The idea is just to get as many of these blue points as possible and get them out over an area of 10,000 square degrees. The volume that we hope to sample with BOSS will be 7 times what we observed with Sloan. Okay? So the idea is to get going in 2009, so there's actually no reason why we can't do that. The Sloan is there, it's working, we want to upgrade the spectrographs, but if we upgrade the spectrographs, we should be able to get going with BOSS in 2009. So this is quite a rapid startup. Get 1.5 million LRGs out where these blue points are, and here I show a prediction of what the power spectrum will look like, and basically the black errors are for a prediction of what BOSS will do relative to the best possible errors from the Sloan. So you see that we should be able to detect this turnover in the power spectrum due to matter radiation quality. The bottom line I want you to walk away with, though, is when we combine with the Sloan supernova, we predict a 1% measurement of Hubble's constant. All right? So if you were to combine this sort of survey with the Sloan supernova, we're now measuring Hubble's constant to 1%, which is truly spectacular. This is my last slide. What do we do after Sloan? We would very much like to do what Sloan has done, but now do it on an 8 nichol. Okay? Sort of a natural progression of these sorts of experiments. One such experiment people are talking about is WIFMOS, stands for Wide Field Multi-Object Spectrograph. This is a proposed experiment on the Subaru telescope, and it's a collaboration between Gemini and the Japanese community. Basically, the idea is with a 1.5 degree field of view, put 4,000 fibers in that field of view. Here are the spectrographs you would need to feed those fibers. And the idea is that you can do about 20,000 redshifts a night. All right, so just to give you a sense of how that's changed, that would be able to do a 2DF-like survey in 10 nights. So it's another jump in our ability to measure redshifts. There is some, the Peacock report for the ESA and ESO pointed out that you need lots of redshifts to calibrate photo Z's. An instrument like this would do that trivially. Okay? So if you try to do that with present instrumentation, it's going to be tough. But so one of the outcomes of an instrument like this could just be the calibration of the photo Z's for things like LSST and Dune. There's lots of other science you could do, And in fact, what I want to highlight is actually there is no reason why something like this couldn't actually be done with one of the VLTs. And there are meetings coming up to discuss the next generation of VLT instruments. I will skip over that and go to my conclusions. My conclusion is we're on target to deliver 500 supernova 1As from our 3 years of observations. This will be a spectacular lowish redshift sample to calibrate the Hubble diagram for the high redshift supernova searches. The dark energy survey is going to attempt to exploit 1As in elliptical galaxies because it looks like those have a tighter Hubble diagram than 1As from other types of galaxies. The baryon acoustic oscillations are now delivering sub 10% measurements of cosmological parameters. And as I showed, it's probable that we're now systematics limited. All right. Is there a 2 sigma discrepancy with the supernova? Maybe this is the first evidence of curvature or a non-constant W. So if I turn out to be right, then I'll be famous. If I turn out to be wrong, then you will all forget this talk anyway. So I'm a win-win situation here. Finally, there is WIFMOS and after Sloan 2 are going to push the baryon acoustic oscillation measurements to about the 1% level. And so there's a lot more to come from the next generation of surveys. Thank you. Yes. That one. Oh, sorry.
The gentleman I spoke to making my imagination overactive. The Z equals 0.2 to 0.35 are different samples.
Yes.
But if it was, this is where my imagination is kicking in, but the points around 0.025 are low, and then there's an anomalously high point with 0.05. No, off the left.
There.
So it was like the high point.
That one.
Yeah.
That is high in both.
Yeah. And then the low points, value would be about half of that.
So you have that point and that point.
Yeah, so those are high points. So if you go to data of about half of that.
With the here?
No, the other way.
That's right. Yeah, these are both.
Maybe.
So,
That's the
so could it just be the systematics of the Sloan footprint on the sky? Is that what you're asking? It could be. I mean, out here, this is very large scales. So the photometric calibration of the Sloan certainly has some impact here. I would argue that the 2DF has been fully here. It's not as much, but it's still a third of the galaxies. And when you look at the 2DF, they also certainly find this extra downward pressure here. I'm pretty sure they don't see that one. So that high point there may be something in the Sloan footprint. But, well, this could be something in the redshift direction. We can look at it. But I think all these are highly correlated. We have done large numbers of Monte Carlos to get the error bars here. And as you see, they're not that far off the line.
So the cosmic micro background, when we look at the first 50 feet, it's kind of nice how we've got on order 100 statistically independent data points going up and down. Not only do these locations get to see the shape, see the theory. Will we ever be able to do that during this evaluation?
So you'll be able to measure that shape.
Yeah, we'll be able to measure that first dip with 100 data points.
So I think there is quite an interesting idea from Daniel Eisenstein and people about doing something called reconstruction. Because obviously one of the problems with the baryon acoustic oscillations is that as that sound echo goes through the universe, it gets pushed around by all the non-linear effects. Now the idea that Daniel and people have talked about is by measuring the local density, you might be able to wind the clock back In other words, sort of move the galaxies back to where they should have been, and therefore you'll be able to sort of reconstruct the original density field. So you might be able to, at that point, start looking at the shape of that field, and actually not measuring the effects of nonlinearity, but measuring. Well, I think you'd have to get rid of the nonlinearities to get at the information in the width of the peak. So once you've done that, I think you will be able to measure something about the peak.
Yes.
Do you have to take nonlinearity of these also into account to get these theoretical curves? So is this purely linear separation theory what we are seeing here?
So this is what you're seeing here is coming out of CAN. So this black line. Yeah. But we have played that one sigma systematic I was talking about. You would want to, this gets dampened by the nonlinearities. So what we do is convolve with a Gaussian, and the width of that Gaussian is, sort of something that you can play with. And so all the numbers I show you are taking into account the dampening of about 10 megaparsecs for that Gaussian smoothing term. Now, when you play with that, the width of that Gaussian, it can change the predictions here, the measurements here, by about 1 sigma. So that's the 1 sigma systematic that we kind of got to figure out.
And then, so can I also with regard to why we asked the previous talk about this 3 sigma and more sigma question? In part, this is very difficult. In part of this interest with different values of W was kind of conceived by theorists who wanted to have some alternative technological function. And then at this time, many years ago, everybody started working on it just because of the work. And they have some hopes. But at the present moment, it looks like if we want to explain technological function, we need containing 120 orders of magnitude, but this can be attributed to, well, principle something. We learned how to do it. Now, if we want to have W different from -1, we need roughly speaking some effective potential of the scale of 2. But the slope of it to be continued with the same accuracy, 10 to the minus 20. And so far, it is very difficult to attribute this slope to anything. And therefore, I would guess that theorists would probably like much more than 3 sigma to be convinced that they should move in this direction. And that's why the 2 sigma maybe not get done.
Well, I think from the experimentalists, getting now the 10% today, getting down to of order 1%, let's call it of order 1%, will be math. It'll be all systematics. And that's going to require...
120 hours.
Maybe, yes. So if you gave us that, I'd say if you gave me that amount of money, I'll guarantee you a 1% measurement comparison. But I think to get down to order 1% is going to require new instruments, because our present instruments are just not up to it in terms of the systematics. Okay, so if you want of order 1%, you're going to have to pay for it. But if you want to pay for it, we'll do it.
Okay, then we will now thank the speaker again.